Hi, we're going to look at a partial fractions problem that's a little bit harder than the previous ones we've looked at. So we have here a rational function we're supposed to integrate, and so we probably go through our little list of, do I know this? No, this isn't one we know. Could I let u equal the denominator, and do I have the right stuff for the du? No, I don't. Integration by parts isn't viable here because you can't factor this into things that are easily factorable or integrable. Okay, so then we get pretty quickly to partial fractions, but one important thing about partial fractions to remember is that partial fractions works when you have a proper rational function. So that works when the degree of the numerator is smaller than the degree of the denominator, and I don't have that here. So we're actually going to use partial fractions at some point in this problem, but we have to do something else first to get this in terms of a proper rational function. So this is a lot like what you might do if you had an improper fraction like 25/3 and you wanted to rewrite that as a mixed number. You would think about how many times 3 goes into 25, and you'd get 8, and you'd rewrite that as 8 1/3. So it's kind of the same idea, but we're going to be doing it with polynomials. So we're actually going to be doing long division of polynomials. It's maybe been a while since you did that. I'm going to erase this. We've got space, but long division of polynomials. Okay, so we're going to take the numerator divided by the denominator. I'm going to set up my division over here. One thing that is sometimes helpful when you do this is if you have any missing terms. My numerator is missing a cubic term, so I'm going to fill in a 0x cubed term there. If you have any missing terms, to fill in a 0 for those terms, just to keep things lined up and so that the degrees of your polynomials all kind of line up neatly in your division problem here. So the numerator, and then that's going to be divided by the denominator. Okay, so then to start this long division, I usually start by looking at the first term out front here in the divisor, and the first term here in what we're dividing into. And so x cubed goes into x to the 4th x times. So think about, what do I have to multiply x cubed by to get x to the 4th? And I'm just focusing on those first terms to start. And so I multiply by x. So I'm going to write my x here. That's what I multiply x cubed by to get x to the 4th. But then to do the long division, I have to distribute that x through to all these terms out front here. So when I do this long division, I focus on the first terms to figure out what goes there, but then I have to distribute through. So I'll have x to the 4th, and then minus x cubed minus x squared plus x. So all that came from just distributing x through times the polynomial that was out front. And then just like ordinary division with numbers, after you multiply, the next main step is to subtract. So I'm going to subtract this entire bottom row. Some people like to distribute through the minus sign. Some people like to just write it out front like that. I tend to just write it out front and then kind of mentally distribute through that subtraction sign. Okay, so x to the 4th minus x to the 4th, that leaves no x to the 4th terms. And then 0x cubed minus negative x cubed will be positive 1x cubed. And then for the x squared terms, I have negative 2x squared minus negative, so that'll be plus x squared, so I'll be left with minus 1x squared. And then 4x minus x, so I'll have a plus 3x, and then I'm going to go ahead and bring down this last term, plus 1. Alright, and then we basically just repeat the process again, looking at the x cubed that's out front. What do I have to multiply that by to get this first term here? And I keep doing that until the degree is less with what I have left in my division problem, and then that'll be my remainder. Okay, so what I have to multiply x cubed by to get x cubed is plus 1. So I'm going to write that in a different color here, just so we're clear about what we're doing here. Alright, so the plus 1, and then I need to distribute that plus 1 to all these terms in that polynomial up front, and then I'm going to write those down here. So 1 times x cubed, 1 times minus x squared, 1 times negative x, and 1 times 1. And then I'm going to subtract that entire bottom row, and then write down what we're left with after that. Okay, so x cubed minus x cubed will be no x cubed terms left. And then negative x squared minus negative x squared, so that'll be plus x squared. There's no x squared terms left. And then 3x minus negative x, so that'll be plus x, so 3x plus x is 4x. And then for the constant terms, 1 minus 1 will be 0. Okay, so at this point the degree of what I have left is less than the degree of what I'm dividing in, so that's when I'm done with my long division. And so I can go back to my original integral and rewrite my original integral as the integral of, and then I'm going to have my quotient, which is up here, x plus 1, plus my remainder, which is my 4x, over the divisor, what we were dividing in. Okay, so there is my long division, and what that basically did was allow me to rewrite the original expression in terms of just a polynomial, the x plus 1 out front. That's easy to integrate. And then the last part that I have here is a proper rational function, so I can then do partial fractions on that proper rational function. The degree of the numerator is smaller than the degree of the denominator. I can't use substitution here, but I can do partial fractions. Okay, so we did a little bit of long division first. There are a few homework problems in your textbook where it tells you, hint, use long division first, but the goal would be to realize why that's what you should do. It's because the degree of the numerator was greater than or equal to the degree of the denominator to start with. So we want a proper rational function, so we can do partial fractions on that. Okay, so I'm going to scroll up a little bit here, and then we'll do partial fractions on the part that we're going to do partial fractions on. So I need to factor my denominator here. This denominator is a little bit more complicated to factor than the previous one. I'm just going to do a little scratch work down here below. I don't have a common factor here, but I do have 4 terms. So I can do what sometimes works when you have 4 terms, which is factoring by grouping. So I grouped this into the first 2 terms and the last 2 terms. I was careful with my minus sign there in the middle to rewrite that as plus and negative, so that when I grouped it I didn't really change how the signs work at the end there. And then with factoring by grouping, you want to factor what's common out of your first group, and you'd be left with x minus 1. And then the whole goal in factoring by grouping is that if you can factor something out of the second group, that what you're left with is the same in the parentheses that's left from the first group and the second group. So I might not at first think there's anything to factor out of that last group, but realizing that I want to be left with an x minus 1 would tell me that I should factor a negative 1 out of this last group, so that I'll change the signs so that what I'm left with there is the same. Alright, so then with factoring by grouping, I treat this like 2 giant terms, and they both have a common factor of x minus 1, so I factor out the x minus 1, and then I'm going to be left with the x squared and plus negative 1 is what I'm left with after I factor out the x minus 1 factor. Okay, so I'm left with x squared minus 1. The x squared minus 1 factors more. That's a difference of squares, so that factors into x plus 1 times x minus 1. Alright, so there we've got the whole denominator factored. One thing that I might notice is that I really have the same factor twice. So I have a linear factor with multiplicity 2, and then another linear factor. So this is a linear factor, degree 1 factor, but it has multiplicity 2 because it occurs twice, and then another different linear factor. Okay, so then I'm going to set up my partial fractions on that part. When I go back and do my integration, I don't want to forget the easy part that was here at the beginning that I also have to remember to integrate. So we'll come back and do that later. Alright, so for right now we're going to work on partial fractions on the 4x over x minus 1, the quantity squared, times x plus 1. So I'm going to be doing 4x over x minus 1, the quantity squared, times x plus 1, and I want to break that into separate fractions. Okay, so when I have linear factors with multiplicity, I need sum of terms here that counts up to whatever the multiplicity is of that factor. So this one's multiplicity 2, so I have two terms, one here that's just x minus 1 to the first power, and then count up to whatever the power is on that multiplicity. So this case we just have two terms here, so x minus 1, the quantity squared, and then I'm going to have another term for my other linear factor, x plus 1 factor, in the denominator. Okay, and my numerators are going to just be constants, a, b, c. Even though I have that middle one with the quantity squared, that's really a linear factor. It just has multiplicity. Okay, and then we'll multiply through by that least common denominator, which is x minus 1, the quantity squared, times x plus 1. And when I do that, when I multiply on the left side here, the common denominator will cancel with the entire denominator, and I'll just be left with 4x. On the right side here, common denominator times that first fraction, I'll be left with a, and then one of the x minus 1 factors will cancel with what I'm multiplying by, but I'll have another x minus 1 factor left, and the x plus 1 factor. And then when I multiply that to my third term here, I guess, so second term on the right side, the x minus 1, the quantity squared, will cancel. So I'm going to be left with b times x plus 1. And I'm kind of run out of space here. For the last one here on the right side, when I multiply that common denominator times c over x plus 1, the x plus 1 factors will cancel, and I'll be left with c times x minus 1, the quantity squared. Okay, so when we've done other partial fractions problems, at this point we've plugged in convenient values of x, and we can go ahead and do that here. It's a little trickier this time because when I plug in convenient values of x to make factors go away, all the factors will go away eventually, and I won't be able to find all of the values. But I'm going to go ahead and do that same way for this problem. Alright, so one of the things that I might try plugging in is x equals 1. That'll make some of my factors go away. So on the left side I'll have 4 equals, on the right side the first term here will go away and the c part will go away, so I'll just be left with b times 2, so that means b is 2. And then when I plug in x equals negative 1, that'll make some other terms go away, so that'll make the x plus 1 factors go away, so the a and the b parts will go away. So I will be left with, on the left side, negative 4 equals c times negative 2, the quantity squared, so negative 4 equals 4c, or c equals negative 1. The deal is that on this problem, those are the convenient values of x that make entire factors go away, but I still need to figure out what a is. So for this one, you can still plug in some convenient values of x. It's just that the last convenient value of x that you plug in may not be quite as convenient as all the others. I'm going to pick 0. 0 is usually a pretty easy number to plug in as long as that's in your domain. So okay, on the left side of the equation, when I put in 0, I'll have 4 times 0 is 0. And then on the right side, all that stuff doesn't really go away, so I have to just think about when I plug in x equals 0, what I will get here. So I'll have a times negative 1 times positive 1, and then plus b times 1, and then plus c times negative 1 squared. So I'll have 0 equals negative a plus b plus c. I have my b and my c, so I can put those in now and figure out my a. Alright, so I get 0 equals negative a plus 1, so I get a equals 1. Okay, so I've got my a, b, c values, and then looks like we are ready to go ahead and do what we were doing here with our partial fractions. Okay, so I'm going to go back to this original integral here and rewrite my original integral. I don't want to forget the x plus 1 part that I got from the beginning, and then my partial fractions on the left side. So I'm going to go ahead and write that down here at the bottom of the screen, and then I'll scroll up and finish the problem. Okay, so I have the integral of the x plus 1, the easy part that I don't want to forget, and then plus, and then I did the partial fractions on the 4x over that entire denominator. So for the 4x over that entire denominator, I had, let's see, a was 1. So 1 over x minus 1 plus my b was 2, so 2 over x minus 1, the quantity squared, and then plus c, my c was negative 1 over x plus 1. Okay, so there is my original integral, all broken up into pieces, each of which I think we should be able to integrate fairly easily. Alright, so that's the integral I want to work on now. Okay, so when I look at this and think this through, I'm really kind of chunking this term by term and thinking through, do I know these? Can I do a u substitution? How would that work? And you may or may not separate this into separate integrals. When I look at this, I would look at these first two terms and say, I know this. This is just basic antiderivative rules that I use. For these next two terms, they're kind of different integrals, but they're actually the same u substitution. You would let u equal x minus 1, and then you would have a du that's dx, so you don't really end up with any extra stuff from those. And then from the last one here, it's a different u substitution, so I'll maybe write w equals x plus 1, and then your dw would be dx. So if you can do all that integration correctly without writing out those u substitutions, that's okay. I'm going to go ahead and write them down here. So I'm really thinking about separating this into separate integrals. The x plus 1, that is stuff I know. For the second integral, I'm going to make the u substitution u equals x minus 1, so I'll have 1 over u, and then plus 2 over u squared, or I might want to write that as 2u to the negative 2 du. So that's for the two terms in the middle, where I have u equals x minus 1. And then the last integral here, I'll have minus the integral of 1 over w dw. Okay, so then I just do that integration, 1/2 x squared plus x from the first part here, plus natural log of absolute value of u. I'm going to go ahead and put my u back in. Use power rule on this next part here, so plus 2 over negative 1 times u to the negative 1. My u was x minus 1. And then the last part here will be a natural log of the absolute value of w. W was x plus 1, and a big old plus c at the end. I might want to clean up just this middle part here, so I can rewrite this in a slightly nicer form. Other than that, I probably wouldn't do too much else with this. Okay, so there we go. So we used quite a bit of algebra there, long division, some factoring by grouping. We had to solve a system of equations, had to think about multiplicity, so there's a lot going on with this one. But this is one that you should be able to do.